Hello everyone. My name is Abhinav M. Today we have done this ontology matching project using machine learning. Our group members are Sagnik, Sairaj and myself Abhinav. So what is ontology? Ontology in the context of information science and artificial intelligence, it actually refers to a representation of knowledge and concepts that captures the relationship between entities in a systematic and structured way. It involves creating a hierarchical structure of categories, classes, and properties and relationships, which provides us with a basic understanding of a domain or subject matter. Ontologies are actually very important for several reasons, which includes the knowledge representation. Means that ontologies actually provide a structured and organized way to represent knowledge, allowing for the model of complex relationships between the entities in a domain. They also provide a formal framework for representing concepts, properties, relationships, which actually helps us to capture the semantics of the knowledge in a consistent manner. Then another important reason is that it is basically used because of its consistency and reusability. Because ontologies actually enable consistent modeling of the knowledge by providing a structured and standardized framework. Also, another important reason is that it is used. Another important reason is because of semantic web and AI applications. Here, it actually plays a very crucial role in the development of semantic web, which aims to enable machines to understand and process information on the web in a very meaningful way. So from this, we all understand that overall ontology is as important as it provides a formal and structured approach to represent, organize, and reason about knowledge and concepts, facilitating interoperability, consistency, and reusability of information, and supporting advanced reasoning and inference capabilities in various domains and applications. Now, talking about the ontology matching. Ontology matching, also known as ontology alignment or ontology mapping, refers to the process of establishing correspondences or mappings between entities such as classes, properties, or instances in different ontologies. The goal of the ontology matching is to identify and align similar or related entities in different ontologies in order to facilitate interoperability, data integration, and knowledge sharing across different systems or domains. So, ontology matching is a challenging task due to the heterogeneity, diversity, and complexity of ontologies. It may have different modeling languages, structures, and semantics. Now, going into the we understand that uh, uh, ontology matching has important applications in various domains such as information integration, ontology-based data access, and semantic web technologies. It enables the integration and alignment of data and knowledge from different sources, facilitates interoperability and knowledge sharing across systems or domains, and supports advanced reasoning and inference capabilities in applications that rely on ontologies. Now going into the main objective of the project. So the objective, this project actually discusses an approach for automatic ontology matching using machine learning techniques. The project proposes an approach that combines different similarity measures between ontology elements as features for ontology matching, and then uses machine learning algorithms to learn these features and predict correspondences between ontologies. The approach described in the paper uses some of the machine learning methods or models, specifically the logistic regression, random forest classifier, and gradient boosting, to automatically compose a matcher based on the similarity measures extracted from the ontologies. Similarity measures are calculated using different approaches, including the string-based, language-based, and structure-based measures, and they serve as features for this machine learning algorithms. Thank you.
Hello, I am Sairaj, and now I will explain the dataset that we have used in our project. So, the ontology files that we have chosen, belong to the Ontology and Alignment Evaluation Initiative libraries, and we have chosen these 12 ontologies to for our project. So the first four are we used for training purpose, and rest we have used for testing purposes. So now I will explain all these ontologies in detail. So, so the 101, 102, 103, 104, these are concept ontologies, and 103 is the language generalization of 101, and 104 is the the uh, language restriction in outline for 101 and 102. So, and the 200 range, these are actually systematic ontologies. So we have selected 204. It has the naming conventions that were not present in 101 and 2, and 205 are the synonyms, and next we have used the 225. These have no restrictions, and 230 it is we're flattening the entities. That is, we are expanding our the components of the classes. So now the 300 range, these are actually the real life ontologies. So like 301, it is the text MIT, and similarly, these are some other real ontologies that we have used for training purposes. And the, from these, the comparisons, what we and the comparisons that we have on this ontologies, like 101, we are comparing it with itself, and 102 were 101 and 102 are like totally unrelated ontologies, and like 101 and 103 the comparison. 101, as I said, is the generalization in our light of 103, and 104 is the restriction in our light. So now 101 and 204, uh, yeah, it is actually comparing by changing its naming conventions. And 205, here the labels are replaced by their synonyms. And in 225, uh, we compare the ontologies by suppressing all the local restriction on the properties. And in 230, in 230, we compare it with 101 by expanding the class components, and in 301 to 304, uh, we compare the ontology by using some real ontologies.
So, hello, I'm Sarin Pasu. Here I'm going to show the model structures. The This is the first function. This read ontology function actually gets all classes and properties from the ontology files that we are passing to them. Then this get mappings function gets all the true matches from the alignment files, and it makes a tuple of both the matched entities using beautiful soup package Python. Then this function getPath, it gets the whole inference path of each entry that's passed into. Then this get dataset function, this creates a dataset for each ontology pair, for each entity pair, for each parent of those entity pairs, and for each path of those entities. Here you can see the data appends the ontology two ontology files. these entity pairs, then these parent of the entities, then the paths of the entities, then matched a value matched if the two entities or the entity pair is matched or not as per the true labels, and if it is a class or a property. Then we calculate feature vectors for each row of the dataset. Here we have used here we have used the features available from this package by string matching dot similarity measure, and we have used all of them and expanded our dataset to contain the feature sets. So we've used also we've also used n-grams and word to vec model. We trained the word to vec model using using Google News data, and also we have used the WordNet from NLTK package to form the feature set. Now we have then we trained three different models. We experimented with three different models. One is logistic regression, second one is random forest classifier, and the third one is XGBoost. So this is the result of using logistic regression model. Here you can see that we are getting best F1 score for this alignment file as 1 with threshold 0.6, and also the best F1 score for this file is 0.98. That is quite good with threshold 0.6, and also you can see the other values also. Uh, by using random forest, we are getting this result. This result set. Uh, you can see the all the values, all the best F1 score that we are getting for each alignment files with for a threshold. And here is the result set for XGBoost model. Thank you.